No, I don't,
It's fine.
because otherwise we get interference with the microphones. That's right. All right, so today I'm going to be talking about gradient-based stochastic optimization under a chance constraint, which is work that started a long time ago. So like in 2008, literally a long time ago, I was visiting, I was in Melbourne, working in Melbourne Uni, but I was visiting Paris. And they had an interesting problem with the equivalent of the NASA. They needed to send, what they call a rendezvous, which is when two satellites have to bind together, whatever. And of course, all the paths are very well, designed. But what happens if there is a meteorite? Or if there is something that wasn't foreseen? So those were the chance constraints. They said, on this, what do? Do we change the current solution and try to figure out what to do now? Or do we just, abort the mission and so on? That was the origin of starting to talk about this. But, after that, I started working in general stochastic optimization. And then I retook this topic in particular. And finally, I've had a couple of students involved. The first one that was involved was when I was at Melbourne Uni, and she was an honors student. And she wrote her thesis on her report and the honors thesis with me on this topic. So it goes back to 2009, 2008. But then I work with some of the students, and there was another paper that I wrote that was published in 2022. And again, that originated on this topic. It originated as a project from the course that I'm teaching. The book that I'm writing is stochastic optimization. And they worked on that, and it was really nice. We got new results, we got new applications, and it was published. But I knew that we hadn't finished everything. So I'm going to talk about it, and I'm going to talk about what have we done after that. Most of the work that I'm doing, I do with my students. Most, you call them postgraduate students. Back in the States, we call them graduate students. All right, so this is like a preliminary that I am assuming that most of you will know, because I'm going to be referring to this. This is when we have deterministic gradient-based optimization. So J of theta is going to be the cost function that we want to minimize. B of theta is called the constraint function. We want the constraint to be less or equal to 0. This is the canonical way of presenting it everywhere. And so one of the techniques to solve this is called the Arrow-Hurwitz algorithm, that I shortened by AH algorithm. And this Arrow is the one that publishes in finance as well. So this is the same person. So this algorithm uses Lagrange duality, and basically what it tries to do is that on the x-axis, which is corresponding to theta, the main control, it tries to minimize. But on the Lagrange multiplier axis, it tries to maximize, and that's why it's called the saddle point. On one dimension, you want to go up. The other dimension, you want to go down, and the optimal point is the one that is called the saddle point. So this algorithm is known to work. I put a little bit of a picture here to understand, in case that you're not familiar with that. What does it mean, a projected differential equation? It basically means that this component, which is on the y side, cannot go to less than 0. So this is known to have a unique asymptotically stable point at the optimal point. So we start with that, and we turn this into computer code. We turn this into a numerical solution for the problem. Euler approximation of this differential equation is going to yield the numerical iterative method for solution, which I just summarized here. So the iterative solution basically takes one step at a time, and the steps have a size, well, we call it the step size epsilon, and it just moves. So this moves in the direction of maximizing the Lagrangian. This moves, sorry, minimizing, that's why it's going down, and this moves in the direction of maximizing. One of the things that I think it's important that you recall is that there's these little primes in here. Those are derivatives. Of course, all my talk could be done with gradients, but I'm just basically simplifying the talk, and I'm assuming that the control parameter is just one variable, but it could be a vector, it could be a bigger vector. So the results that we're going to be using that have to do with, that will be pushed into the stochastic optimization is that, well, first of all, we have an ODE on one side, which is this ODE. The solution to this ODE is two functions. These are functions of time. So the time is continuous. These are discrete sequences. So they live in separate spaces. So how do you compare apples and pears? First of all, you need to use the same metric space so that you can define distances between processes, and then you can say if they look close or not. That's why I'm going to be using interpolated processes throughout my talk. The interpolated processes takes these points, and it does the same thing that, you know, when we had those dot printers, we used to print. And of course, it looks like a solid line, but the printer is basically just printing different dots. So these interpolated processes are going to do the same. They're going to basically join these dots to define a function. And those are the functions that are going to converge actually in the subnorm to the solution of the ODE. So the solution of the ODE gives us the solution to the optimization problem. But in order to get the solution of the ODE, we go through iterative method, which the computer can deal with, you know, with iterations. This is the basic thing that we all know. And this is my building block. And then we're going to be adding some stochasticity into it. So the visual for the problem formulation is called optimization under chance constraint. Say that you want to optimize something and the absolute optimal is your target. And you want to reach the target, but you don't actually reach it, you know, with probability 1. You're shooting, but it doesn't actually shoot with probability 1. So if you aim at that target, the actual point where it ends is a random variable, and 90% is, you know, centered at the target would be this area. But the boundary safety region tells you that you have to be in this region. So there is a big part of it that wouldn't satisfy certain constraints. A chance constraint tells me, I know that I might fail, there might be failure, but I want to minimize the risk by saying, I will admit failure with a probability of, say, 0.05 or 0.005. So you do the limit. You say, this is as much risk as I can take. So that's the type of problem that we have. So what do we do with that problem? Oh, it's funny that, yeah, well, I had, I have a shadow, but it doesn't show. So what we do is that now we shift the aim. So we're not aiming at the target. We will be aiming somewhere else so that the constraint will be satisfied. Yes.
So the dotted lines are here. So suppose that you've said that your red target with the one circle, the one surrounded by the blue line. You have a 95% chance that your actual result will be within the blue line. Okay. Is that correct?
Yes and no. Say that you have a hose for the garden. Yeah. You're aiming it at the target, and you will have drops of water around that target. Right. Those are the blue. That's the blue line. Mm-hmm. So instead of aiming there, you aim elsewhere, you aim here. And when you aim here, you still have some, droplets everywhere, but at least you're not going to go into your neighbors or something.
Right, so you're guaranteed that everything will be within the document.
Yes, not everything.
No.
This is 95%.
Right, okay, so I guess the next question I have, got that bit, is that if you somewhere in between the blue circle and the yellow circle, you would have a situation where within the circle, there'll be a little bit within the circle, but outside the safety region. But conversely, on the far side of the circle, if you happen to be outside the 95% in that direction.
Oh, that's no problem.
Yep.
Yeah, I mean, if you eat a certain amount of poison, you die.
Yep.
But if you eat less, you don't mind how much less you eat, you're not gonna die. So you're well inside the bounds.
Yes, I guess just the point I was trying to get at is that, that you would reach 95% confidence even while a particular circle within.
That's right. That's why it's a minimization problem under constraints. It's not just satisfaction of constraints, but you want to see if I have to satisfy the constraints, what's the best I can do? So what is the best in terms of hitting the target that I can do, but with the constraint that I cannot go beyond this green line with certain probability. That's right. So just to give you some ideas, this problem was a problem that was taken to the École des Ponts et Chaussées in Paris by the electricity company. They wanted to know how do they control the dams so that they want to open for recreational activities in the summer with at least some probability. It was the time when they did the beach at the Seine, at the River Seine in Paris, and it was like a new thing. And they realized that it was very important for tourism. But if the dam is used for electricity and for watering fields and everything, then they might actually not have enough water for the summer recreation things. And so they wanted to know how to control that, ensuring a certain probability that it will open for the winter. Another application that came when I was working here with Owen Jones at Melbourne University, and this was CSIRO. So they wanted to look at wind farms, and they wanted to know about batteries. We were working on that together. So the thing is that the windmill batteries have to control how they release energy or not, because they need to avoid bursts. And of course, in wind farms, wind is very bursty. So this is a real problem. And so they wanted to avoid the bursts and surges in electricity that will cause problems. So that's another problem. And another one that we published in the paper that I told you, 2022, with some of my students, they were looking at robotic arms for surgery. And so basically they say, if we're manufacturing a robotic arm for surgery, and it might be sending some laser or something that may cause ablation in the tissues that are around it. But if there is an artery close or some kind of, very important area that shouldn't be touched, then the robot should be able not to actually aim at the target, but aim somewhere else so that it doesn't cause more problems. So that was another application that we have. So now, yeah.
But isn't it, doesn't mean that we add some margin to our constraints. Yeah. So we really optimize against some distribution, probabilistic distribution.
Yeah.
So
Yes,
simply adding a margin.
Yes, we do. Yeah. So this is the mathematical formulation. So I finished with the story. Now comes the math. So this is the mathematical formulation. We have J of theta will be our cost function like before. But look, the constraint function has become a probability constraint, a chance constraint. The probability that the thing is going to be less or equal than alpha has to be bigger or equal to P. We call this the safety region. The G less than alpha is the safety region. So the probability that it is within the safety region has to be bigger or equal than some probability P. The control variable is theta. We assume that is a convex cost function. The C here is a random variable or process. We will see later that we can imagine that there's a process, and there's a convex safety region that is the real valued function. So the main problem, so I've already told you, sorry, I forgot my line. So I've told you why this is important. I've talked about 3 possible applications. They're very important. Now I need to tell you why this is difficult. Why is this challenging? Why is it elusive? Why is it hard? Well, there is the problem that the constraint function now is a probability. Okay, this is a probability function, and the probability functions are neither convex nor concave. So that's one problem, that we don't have convexity. There's other problem that we identified in the paper in 2022, which we call the vanishing gradient. Distributions have flat areas, and in those flat areas, the derivatives are 0. And so algorithms that are based on derivatives do not work very well in those areas. And there's other types of problems, you know, with these probabilities. Probabilities are between 0 and 1. When we're working with computer algorithms, it's very possible that they go beyond the boundaries. So I have to truncate them. And the moment when you truncate, you start getting very unstable, you know, behavior. So there are many problems with the probability constraint formulation. So the existing approaches are either we convexify the distribution functions, or we take another risk measure. That's very common in finance. Instead of taking the probability of, you know, the portfolio falling from a particular value, you take the C-bar, you take other approaches that do not have that problem of the probability. Now, in one-dimensional problems, we proved that the quantile formulation not only works and it doesn't have the pathology of the probability constraint, but it is also convex and it is provably convergent. And so we can use the quantile formulation instead of the probability formulation. And there are more recent papers as well, where they look at chance constraints and they also realize that instead of stating the chance constraint as a probability function, they do it in the terms of the quantile. So it is recognized now that the quantile formulation might work much better. So what have we done? Well, I'm going to tell you in what we've done. I want to tell you, I deal with a simple problem, and you can see there's a simple model, general model, and so on. The simple model is one-dimensional. In the simple model, under monotonicity, the original problem, which is a probability distribution, is equivalent to the function g, but now it's evaluated at the quantile. So this becomes deterministic. This is no longer stochastic. And so in that case, we can just, you know, we proved that the quantile formulation is a convex nonlinear program. Actually, I proved it for the Arrow-Hurwitz algorithm and also penalty functions. And today we're going to see also projection methods. So it actually does work very well for all of those methods. And so these are provably convergent. We've already done that, so that's known. So what's the challenge? Well, what if we don't know the quantile? If we are streaming data, we don't know what distribution it's coming from. So if the quantile is the inverse of the distribution function. So if we don't know the function and we just have data, then we need to estimate that. So that's one challenge. In the multidimensional case, we have, the problem is a little bit more complicated because now the variable C is not necessarily a random variable. It might be a vector, it might be a whole process, it might be something really complicated. But the function, the safety function is a real valued function. So when we define this random variable, this is well defined, even if this is a vector, this is a well-defined random variable with a distribution that is in one dimension. So in this case, the problem is becomes the problem of simply the quantile as the constraint function. And of course, the problem here again, we don't know the distribution f sub theta of this random variable. So we need to estimate that. If we, so existing approaches for this are statistical estimation. They use a tremendous amount of data, and they do statistical estimation of the distribution function, which of course can be done relatively easy. But then what they do is they use kernel approximations to have these functions as functions of theta, because that's the problem. They are functions of theta, but we don't know how they depend on theta. So they use approximations, and then they need to invert it. And then they need to approximate even the gradient with respect to theta. So these works are amazing. They're really, really good works, but it requires a tremendous amount of steps in all these algorithms. And they're basically taking the static point of view. They have the data stored and they do the optimization. I want to do reinforcement learning. I want to do something that I keep getting information and I keep obtaining what is the best data for that information. So it's different. It's a different approach. So the challenge here will be how to estimate the derivatives of the quantiles, and can we reduce computational complexity? Those are the challenges that I'm going to address today. So the contributions that we've done in this talk. For the simple model, we have used observations in order to estimate that quantile, because we assume that we don't know the quantile, and we have several ways to estimate these quantiles. And by doing one little trick, we were able to reduce the computational complexity from n log n to n. So basically, amortized analysis tells me that I go from log n to order of 1. So meaning each step is going to take the same amount of time. And so that's one of the contributions. And of course, we have analysis of stochastic approximations. I don't think that I'm going to talk about the 2 timescales in this talk. It's a little bit more detailed. And if you have questions, you can ask me. And then the general model, which is the one that I like the best, of course, because it's the more difficult one, but the more realistic one. Now we have a vector or a process, and there's a function zeta, which is real valued. And this function zeta is the one that defines the safety region. This is the one that has to be smaller or equal than some quantity alpha. So what we've done, we've developed the derivative estimation for the quantile by only looking at the data that is coming. So you have C1, C2, C3, you have observations of the data, and you need to estimate not just the quantile, but also the derivative of the quantile. So that's one of the things we've done. And then I implemented stochastic approximations for concurrent estimation and optimization. And we proved the results. Now, again, this analysis of computational complexity, and that's going to be at the end when I say complexity reduction, because we solved the problem, but it was basically impractical. The computational requirement was too big. So we have some alternatives for that. Okay, so now we go into the simple model. In the simple model, remember that what we want to do is to solve this problem, minimize J given this constraint. We don't know Q of P,
right? We don't know the quantile, but we have samples, CI. So what we do is order the samples and take like the 80% sample there. That will be what we call the sample quantile. Same thing as the sample distribution function. And if we use the sample quantile, it's very well known in statistics that it converges. There's a central limit theorem for it and everything. So we know that it converges. So fine. So I'm going to just replace. Instead of the constant Q of P that I don't know, I'm just replace the estimate. And we can prove that it converges in distribution, it's weak convergence of stochastic processes, and it converges in distribution to the solution of the Arrow-Erwix ODE that I showed you at the very beginning. So all is well with this, or isn't it? Well, the science things. I need all the sample. So at step 100, I need 100 observations. At step 200, I need the 200 observations. So in principle, the memory explodes. I can't really continually work on this algorithm because the memory requirements are going to make it explode. But also, there is an insertion at some point. Every time that I get I have a sorted list. Every time I get a new observation, I just insert that. And at best, I mean, it was funny because I was working with this student and well, he was my former student, but he's already finished. And he told me, look, I was working on Python, but it turns out that Python doesn't have log n. It's much slower. It must be doing linear search or something. So he converted everything to C, and he actually did the binary search to insert something in log n. So, this is also something important. What data structure you use, what compilers are you using? But anyways, at best, if you have a list to insert in that list, normally you have log n. So log n at every step. So to get to that step is n log n. So this is bad. Memory requirement is big.
May I ask, do you want to know your quantile distribution with an unlimited precision or in a
You're totally right. Yeah, the
or-
beams and everything. Yeah, I know. Yeah, we can talk about that later because this is something I want to explore. Yeah. So let's try to look at something different. I want to estimate a quantile. The quantile is the inverse in the distribution function. So if this is my distribution function and this is P, then the quantile corresponding to P is the one here on the x-axis, the inverse. Because distribution functions are monotonic, increasing always, I can say, well, if I am above, then I can just tell my algorithm to go back. And if I am below, I can tell my algorithm to go up. And so that way we do what we call target tracking. So target tracking algorithms are very well known. And what we do, this ODE is basically telling me that the movement that I'm going to have is exactly like that. I'm going to try and hit the target. When it hits the target, the right-hand side is 0. So the ODE doesn't move. It's arrived at the optimal value. And this is the Euler approximation to that with stochastic observation, because the expected value of the indicator function is the distribution function. So this is basically the mimicking that equation into the stochastic approximation. And what we have, and so, yeah, so the interpolated process, again, the one that converges in distribution to the solution of that ODE, so everything is fine. This is to estimate the quantile, but we don't want to estimate only the quantile, we want to do the optimization. So what we do now is, well, I'm gonna skip that one. So what we do now is the following. I would like to have this algorithm with the Q of P here, with that constant. but I don't know it. So I'm gonna add an extra level that tells me I'm gonna be tracking the quantile. So this is concurrent estimation of quantile and optimization. And yes, we have the result that it does converge. It converges to this ODE, and this ODE tells us that everything is fine. This ODE tells us the limit of this ODE has a unique asymptotic point, and it's the one we want. It converges to exactly what we want. In each step, in the stochastic approximation uses only the new observation. This is important. There is nothing here that depends on further past. It only depends on the current value. So instead of log n or n log n, we go to order 1. It's very, very efficient. So we just, and we don't need to keep memory. There's basically just the new one that is coming on. And then the computational complexity is much reduced. So that's what we have with the simple model. Okay, not going to go into 2 timescales. It's a little bit technical. So I'm just going to tell you there exists a way to accelerate with 2 timescales. It's the same algorithm. It's still, memory order 1. It's still very efficient. But look at this. The blue line is what blue and these lines are the original one that take the sample quantile. We know that it is going to converge to the optimal value, but we also know that the memory increases ever again. And so it's inefficient for something that goes on and on and on. The target tracking does really well, and it goes to there as well, but it takes longer to converge. It takes more time. The 2 timescale is like a compromise between the 2. It hits very quickly, so that's the purple one. It hits very quickly where we want to be, but it has a little bit more variance around it. So that's more or less the way that these 3 algorithms would be working. So
can I just quickly check? I know you don't want to talk about a 2 timescale, but 2 timescale with reference to the random variable being measured on 2 timescales. Is that what you mean?
It's the iterations. It's the algorithms.
The algorithm. Okay. Yeah.
Yeah. You think about the time, the iterations as being time.
I see.
And so you want the queue to iterate faster.
Yeah. Okay.
To arrive faster.
Yes.
And you want the other one to go slower. So that's more or less what it is.
Yes. Okay.
Yeah, this is more or less what I had. So one of them has to go faster and the other one slower. Yeah. Okay, so we're going to go now to the general model. The simple model was basically just to warm up on the kind of things that we're doing. So the general model has, we can see the shadow here more or less. So it has a stochastic process or vector. The safety function, again, is a real function, but it is a real function of this process. The constraint is still the same one that we had before, and the quantile will be the inverse of the distribution function of these random variables that we don't know that. So what we know, the observations are C, and we do know the function G, so we can apply the function G. In this case, this is basically what we want to do. This is the problem that we want to do. All gradient-based methods are going to require not just the estimation of the quantile. We've seen more or less how to estimate quantiles, but it also needs the estimation of the derivative of the quantile. So this is a new result that we just have. In our paper is called theorem 4, so I basically just call it theorem 4. So instead of giving you the theorem, mathematically and all that, I'm going to try and do more like a pseudocode, visual pseudocode. If you have these observations, then from each one of these, you can calculate the corresponding safety. So you have a vector like that, a tuple. Now, you're going to define the order statistics with respect to the lower part. And you sort the vector with respect to the lower one. And that gives you the sorted one that tells you the xi is the one that gave rise to z1, the x2 gave rise to that one. All right. Now, the estimation of the quantile is the same as before. That's exactly the same. And the new result, which was rather surprising, and some people didn't believe that this was right, but I think it is right, and I proved it for some conditions, is that the derivative of the quantile can be estimated in this way. You just need the derivative of that function, which you know because it's your safety function, but you have to go back to see what was the original variable that gave rise to this other number. Now, in the proof, I was a little bit confused at some point because there's uniqueness from here to here, but there's no uniqueness from here to there. So for one value of z, there may be many different values of the x's that could yield to the same value. So that's why the best I could do is the QM will converge with probability 1, but the best I could do was the DM converges in expectation to the derivative. But they do converge, they work. And so what we're going to do, well, and again, this is about sorting. So I couldn't get away with the n log n. This is still, you still need all the sample and you still need to sort it out. So this is the computational complexity. So what we do, well, this is the, this is showing you that the derivatives actually do work. In here, we have different values of theta, and we're using p equals 0.8, which is, the extremes are generally the hardest to estimate. And so this is, we did a lot of experiments, and in all of them, it actually works very nice. Again, we have a table that shows that the numbers do coincide very nicely. For different values of p and different values of theta, we use that algorithm, and it works very well. So what we do is that we aim that Arrow-Hurwitz deterministic algorithm, and we replace. We don't know the derivative of the quantile, so we put the estimator. We don't know the quantile, so we put the estimator. And so when we do this, we actually can prove that this algorithm, which is called a stochastic approximation, will indeed converge to the solution of the Arrow-Hurwitz ODE. However, the computational complexity is very bad. I told you that to estimate this derivative, I needed to have the whole sample, right? Mm-hmm. The sample of the z, and order it. Now, when I change theta, I need to recalculate the z's. So it's going to be n, I have to sort it again. So it's not just inserting, but sorting the whole new list. So this is actually n squared log n when you go into that. It's really, really bad. So it's very slow, but it converges. And again, I need the same kind of memory. So this is, one example where it converges, using the insertion method. So now we go into my last chapter, which is, okay, everything is working, very clever. We could do the quantiles, we could do the derivatives of the quantiles. It seems to be working, but it's not computationally efficient. It's very slow. So what are we going to do? So we explored different ideas. So our algorithm converges, but not in very good computational time, the running time. If we deal with reinforcement learning, then the ideal is that the running time should be just 0.1. You should just go boom, 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 and forget the past. You just go working. And the memory requirement should not grow either, should be sublinear or just like that. Because, of course, if you have to store more and more and more data, then at some point it's going to explode. So we need to find ways to do complexity reduction. And we did 3. One of them is exploiting monotonicity in case that it works. And we can go from n squared log n to n log n. It's a savings, not very substantial, but it's a savings. But it's quite nice. And the other one is to do a sliding window, which is more or less what you were saying. Why keep all the sample? Just keep the last 100 or something. Now, let me just tell you, the problem with the sliding window is that you keep the previous 100, but because theta is changing, the sample changes. So you do need to evaluate those 100 anyways. Those 100 samples anyways, every time you change theta. And then there's one that we have 2-stage optimization that is not applicable all the time. But it basically says the following, which is very well known in nonlinear optimization. If you know that the constraint is active at the solution, just track the constraint. Just try to solve, what we call an inverse problem. Try to solve just for that condition. So I exploit these 3 different methods. They're not perfect. I don't know how much time do we have?
Probably about 10 minutes.
Yeah, well, so I'm just gonna tell you more or less what I did. So the insertion method calculates for theta n plus 1. The insertion method needs the new sample, needs to recalculate the whole vector, and needs to sort the vector, the whole thing. If we have monotonicity, then for different values of theta, the 3rd point is still going to be the 3rd point for another value of theta. So we just need to sort with respect to a theta zeros, a baseline. So we have the vector, we keep a vector, which is evaluated at just one fixed value of theta. When we get a new observation, we insert it where it should go for that value of theta. But we only need the pth number, and that pth number is obtained from theta 0. So we need only to calculate the new value at theta n plus 1, only this one. So there is a tremendous amount of complexity reduction when we can do it this way. So basically we reduce it. What I'm not taking into account with these growth rates is the fact that this only calculates one more value, whereas this one needs to calculate the whole vector. And that also adds seconds of operation. Of course, n plus n log n, it's still n log n. So if we're going to talk about rates, it's still n log n. But in reality, this adds n more every time, whereas this one just goes into the log n. So that was one way that we can do it. The other way that we can do this is to say, I'm just going to consider m observations. M is fixed. And so I'm going to still have to sort all the vectors, but it's not growing with n. So the next step, I still only just take m in the past that I have seen. And that's what we use. The result is that we still can prove, that the corresponding stochastic approximation converges in distribution to a solution of an ODE, but the ODE is not the optimal ODE. Now there's going to be an error at the end. And the error is an error that you're not going to take away, because it's an error due to the fact that you have a limited amount of data every time. So there's going to be an asymptotic bias to that. We have some figures to show that, the asymptotic bias as well, but I didn't include them here. So what does this graph is telling us? The monotonicity is the blue line. The windows with different windows are increasing in size. So it's a little bit slurred, but we know what the optimal solution is. And the thing is that with the windows, we have a bias. Except if the window starts getting bigger and bigger, then the bias starts decreasing. But look at, this is the runtime in seconds. This was iteration numbers. If we increase the window to 100 or 1,000, it means that every step is taking 1,000 times more seconds than the other methods. So we can see that the window with m equals 100 looked really nice in here, but it doesn't look nice in here. It takes a lot longer. It's much slower. So the other ones have the trade-off that if we take a very small sliding window, we do the algorithm really fast, but then we have that asymptotic bias that is not really going to get to the optimal value. I do a remark because obviously, if we do have monotonicity, we could combine the two. And combining the two methods would be probably a lot more efficient. We haven't done that yet, but it will be nice. The final thing that I did for complexity reduction was I kept thinking, how can I get rid of the sample quantiles and the sorting and the insertions? I don't like that. And so I thought, how can I get back to that tracking? That was really efficient. So it occurred to me that I could do 2 stages. First of all, find the original unconstrained optimization. If it satisfies the constraint, then you're done. If it doesn't, then the constraint is active at the optimum. And then we basically just have to find theta to track that problem. And this is again a target tracking problem. So no derivatives, no, unfortunately for me, because I really like that theorem, but we don't need derivatives, we don't need sorting, we don't need anything like that. Now this is interesting because we have to put it together. This first equation is tracking the quantile itself. But the second equation is trying to track the theta that satisfies this equation. So it's a double tracking. So you're changing one thing and then you're changing the other, and that changes the other one. So that's the target tracking, concurrent target tracking for both of them. But we were able to prove that again, the interpolated process converge in distribution as epsilon goes to 0 to these equations. And then I actually had to prove that these equations do have a unique asymptotically stable point at the optimal value. So, it was relatively easy. You just work with the eigenvalues and you work with your ODE things, and it works. So the nice thing is that the computational complexity here is basically just the order of 1. So in this case, we target both of them. And again, just, you will like this. We did do the 2-time scale. So yeah, so we do I took it out, the 2 times. Yeah, this is the 2-time scale. And the 2-time scale should actually work much faster as well. It has more wiggly at the end, but it usually works much faster. So we focused here on convergence and computational complexity, which is something that I haven't seen in other papers. Like other papers are really using all data, and they must have access to hypercomputing machines and things like that. So I focused on something that, how can we make it faster? How can we make it easier? Concurrent estimation and optimization via target tracking is one of our contributions. Results can be applied to other methods for optimization, such as penalty methods and projection methods. So the results can be generalized. And also, one thing that is very important, when we do stochastic optimization, generally we don't know the function j of theta either. That is also an expected value, the cost function is also not known to us. That can be added, and it's basically going to be the same results will apply. So future work, I don't know what would I do if I had several probability constraints, which I might have with you, right? So we might be going into the future if we want to consider more than one probability constraint, as it would be, for example, in your project, and that would be really interesting. I do, it's just a selected, I teach basically masters and PhD students in New York, and I have developed basically these courses. And so the way that I do it is that if the course has 14 weeks, I'm probably going to be lecturing 8 or 9. And then they choose projects. Mm-hmm. And then we work on the projects, and we meet and we discuss and we see how do they apply the methods that I have taught them during class. A lot of these papers have come out from those courses. So a lot of these ideas have come from the students, and I've published with them. So I like to do that. I think it's great to work with the students anyways. All right, so this one is on computer vision. And in this one, the computer needs to basically find what are boundaries, right? What is a tree and what is a wall? Is this a floor or not? So we were using the usual thing, the cameras that basically have the point, and then you figure out vectors. However, put a tree in there and it becomes a stochastic, because the computers that are basically just looking at the deterministic thing, they're going to find a leaf. So they're going to think the leaf is a wall, and then they're going to find empty space, and then they're going to find another leaf. So we had to introduce a particular distribution for the fuzzy stuff. So the fuzzy stuff is like trees typically. So what do we do? So what are the methodologies that we use here? Stochastic approximations to optimize change point detection algorithms, which is something statistical in statistical analysis. And so we use statistical methods, supervised learning, and applied probability. That's the kind of things that we used. Tom Flynn was our student, and the other 3 are the professors in the math department and the computer science department. But Tom is the student who basically had this idea.
When you say change point detection, you're talking about sort of satellite imaging changing over time, recognizing forest.
The change point detection is a hypothesis test that is asking you, are the random numbers that I'm seeing here coming from the same distribution, or has it changed? Yeah. So when it detects that something is not exactly like it used to be, it tries to find where was the point that changed.
So it's images over time.
No, the time here is basically each of the probes that we're taking. Yeah.
Can you count them? Because my friend is working for Australian government on counting trees.
Oh, that's interesting.
Yeah.
I don't know. I don't know if you could do
you're just outlining the bounding boxes. Yes, not counting.
Yeah, that's interesting. Yeah, that's interesting. So you want to use clustering or something like that?
Yes.
Yeah.
Need to count this green mass split into distinct trees.
Yeah. This was a very interesting project, I believe. So this is a chemical reaction. It's in biochemistry. Basically, our bodies have an internal way to detect circadian rhythm, daily rhythms, not just by light. That's the important thing. There are some organs like your liver or your heart that should be able to work even if you're not seeing the light of the day, and you still feel sleepy at night and waking up in the morning. So how does that happen? There's an activator molecule, there's a repressor molecule, and I'm not going to explain the whole thing, but basically the way that this is done is that a concentration of certain proteins is going to trigger the messenger RNA to produce more protein or less protein and things like that. So with this scheme, we had basically, well, that was Alexei's idea. And so with this scheme, we had the way that the activator and repressor go like that in waves. So our question was, when it's not 24 hours, what are the optimal rates? We thought this could be personalized medicine. If we can actually identify which are the chemical reactions that could be accelerated, maybe that can inform pharmaceutical companies to know how can they help, ease these type of problems. Not that I have worked with them, but we thought, this could be a first step. So basically, we modeled the problem as a multidimensional birth and death process. So this is basically your Markovian type of, chains and everything, and you're using the standard clock model for simulations and things like that. We did a little bit of a theoretical analysis where we compared to ODE models, and we actually have a result that explains when the two models are not equivalent. So that was published. And again, Alexei was the student and I was the supervisor. So we use stochastic optimization as well. So those are the techniques that we were using there. This was nice. There was what was it? Well, it was 2014, something like that. Harvard came out with the idea that they were going to do these robotic bees. And the main idea to do robotic bees is they wanted to mimic collective intelligence and try to learn from it. But also, they can pollinate fields. When there is a colony collapse disorder, the bees basically deplete. The queen is no longer there. It's really terrible for the population of the bees, and that is happening all across the world. If they survive, then they find that the fields are no longer there because they haven't been pollinated. So it's doubly devastating. So in order to help the real bees to come up and resuscitate, whatever, rebuild their hive, they send the robotic bees to pollinate, while the real bees can't do it. Now, it was very interesting because, again, these students in a project of mine, that was the simulation course, they said, how do we control the flight of thousands of robobees back to the hive? These things are small. They're extremely costly. And if they collide, there's no real bees. You collide and you basically say, give me some space. But these bees basically break. So you don't want them to break. So our problem was, how are we going to send them back to the hive? And the other problem was, of course, they need to communicate, but everything that you put in the bees, like GPSs or other things, are weigh a lot. And so flying these things is not a trivial thing. So we use cloud computing. We basically use the signals of the bees, were just location signals, very, very minor kind of information. And then, of course, the signals have noises, and we needed to figure out how to solve the problem. So again, we used a little bit of stochastic analysis, applied probability, deterministic optimization, and differential equations. And here the student was Silvano Bernabel. This one originated with a project with Natasha Bolan at the Melbourne airport. So this originated here. And this is one where we have two control variables. One is an integer one. So each of these plots corresponds to a different integer. And the other one is a continuous random variable. And of course, the plots correspond to that. Now, this is a deterministic view, but everything had to be estimated. So again, we use statistical analysis of convergence and so on. This is deep learning that I did with Danielle, who is right here, sitting there. So in here, we took, I was going to say the brains. No, we took brain images we didn't take the brain of anybody. We took brain images and we were working with Dr. Amen, who was basically the director of that clinic. And he was at the time interested in mostly ADHD, depression. What else did we do? Depression, ADHD. There was something else. You don't remember, oh, it doesn't matter. So we had like 4 different conditions. And so we wanted to do this deep learning. And so we try to use simulation in order to fill in the data that is missing, because most people that are healthy are not going to go and pay $5,000 for a brain scan. They don't need it. So we had very few samples for healthy people. And there were a couple of other things that we also did in there. So mixing a little bit there regular. So the other project that I have, and as you can see, Silvano is my co-author in many of these papers because he's my PhD student. So he's, we work with many different projects. So here, the problem is simulation. So simulating a transportation in a city is really heavy. If you try to follow each individual car, I mean, look at his face. No, it's just impossible. So we're trying to find methods of decomposition that would be applied. And for that, we use theory of Markov chains. It's actually singularly perturbed Markov chains to try and decompose the system and make it more efficient. So this is another application into that. This is something that I did. Liu, Srivastava, and Juan were my students here in Melbourne during the COVID. So I came here for a sabbatical and COVID hit, so I stayed a little bit longer. So I was teaching here at the CIS, and they wanted to do something, using the methods that we were looking at in the course. And so what they did was they used a lot of data, and what we basically realized is that the estimation of this is like a typical epidemiology compartmental model based on this SIR that most people now have heard of during the COVID pandemic. So it's an ODE that describes the pandemic, and then you try to fit the parameters. And we were fitting the parameters and they were going well, and then suddenly the parameters were going that way. But the data was going another way. So basically what we realized, we're at a time, it's not like the plague. We're at a time when governments suddenly told us that we couldn't go more than 5 kilometers away from home. Remember that here in Melbourne, we couldn't do that. We couldn't go to Sydney. We couldn't go. So if you impose those conditions, obviously, the ODE will have different parameters. So what we did was that we do change detection methods as we do concurrently with the statistical fitting to try and figure out, is my equation changed or not? And it was funny because that we actually predicted the Delta variant before it was described. So we saw that it had hit already by using the data. So that was another thing, and I did it with the student from here. And again, more viruses, of course. During the pandemic, I had a couple of things. Alex Ying, Pauline Lin was a professor here. So she was she was a lecturer here. So again, mixed group with Melbourne. So there was a paper that said that the subway in New York, this is the subway during the COVID. I should have shown you the photo before. I mean, before is like, really you can't fit in there. There was somebody who said in the New York Times that the subway was the major disseminator, if not the principal transmitter. And the mayor immediately sent, no, it's not true, blah, blah, blah. So there was a controversy. So what we did was simulation models, but we do a continuous time Markov chain for the transmission of the virus. And then we do the whole simulation along one subway line called the L line in New York using data. Our findings was that, yes, you could get the virus riding the subway. And then again, also with Danielle, we did a study for optimal vaccination policies. And then we use semi-Markov process models, biological models of high probability, and a lot of simulation as well. And this is our student. So our student also worked with us. And this different is right there. So courses that I have taught or developed, stochastic optimization, and the textbook is now in press, so it will be appearing. And that's the course that I taught here in Melbourne like 3 years ago. And then I also develop the materials for computer models and simulation, and that's it.